I pray that we will be able to listen to Josep. Josep, would you like to try to speak?
Yeah, hello, good morning.
Hi,
well?
it works.
Okay.
Okay, go ahead. It works.
Okay. So welcome from my side. We will have a brief presentation about the decision support tool mentioned by Sergio. It will have very few slides, so we will give some kind of background of what the decision support tool does, and then a more extensive, more extended live demo that you will see how we can use the tool in live, in real time. So I will share the presentation with Athina Timpakianaki from EMSAN. So these are the principles, and this is the main structure of the tool. The first principle that we decided to adopt, it was to have a user-friendly tool. Models can be quite complex, and many cities, many public authorities do not have the knowledge to not to use them, but to understand, to fully understand what a model means. It's what Reda was mentioning. It's not about knowing the future, but it's about understanding how people behave, and we can try to understand what will happen in the future. So this was important to you to build an environment that it was friendly for the users, not requesting data science skills, not requesting transport modeling skills, just a very basic knowledge on how to use a web platform to enter some data and to run some processes. The second principle that we wanted to respect was that the tool should be useful, should be of interest for any kind of city. So we didn't want to have a tool that with many requirements in data, in models, in local knowledge. So we wanted to build a tool that it can be used by any kind of cities. And these are the three levels that you can see here, and it was in the slide of Sergio. So level 1 is aimed for a city with no model, with no data or few data about the mobility and layout in the city. This means that, and you will see live how we will use level 1, it can be used quite easily. You only need very aggregated data about your society, so an estimation of the demand, value of time, walking speed, cycling speed, so very aggregated and standard data that if you don't have it for your city, you can take it from another city or from the literature review. Of course, the lowest the input requirements, the lowest the details on the output. But still, this level is giving to the city a preliminary understanding of how on-demand or shared transport mobility services could work in their city, and very initial insights on how many stations, how many vehicles they need. Next level is level 2. Level 2 is something between level 1 and level 3 in the sense that we still don't need a model, but we need some more detailed data. We need origin destination matrices, we need trip data, we need the road network, the public transport network, the bike network. So we need more geographical data. Having this more rich input, we can have, of course, a more rich output, in the sense that level 2 is optimizing for a concrete demand the best supply configuration, meaning that if level 1 was telling me 20 stations, level 2 is telling me the location for these stations. Of course, all the levels are sequential. So it means that any city can use level 1, then level 2, and then level 3. And indeed, from every level, we are taking the outputs to the next level. But any city can use only level 1, only level 2, only level 3. So any kind of combination of levels, it can be done for the city. Finally, level 3 is the more complex. And here I should mention that level 1 and level 2 are online. You will see how we will use them in a few minutes. And with a few clicks, the city can, or the user, the operator, the authority, with a very few clicks, it can have a result in terms of how many stations, how many buses, how many bikes, the location of this station and these bikes. So it runs live as it is used. While level 3 is offline. Level 3 is the result of all the developments, some of them presented by Sergio and mentioned by by Javier, all these developments, all this new modeling, the hybrid approach, agent-based simulation, everything is going into level 3. But this level of complexity means that it cannot be something online. So we need an offline support by a local partner. It can be a consultant company, it can be a university, it can be a research center. So level 3, in the sense of the tool, is only facilitating the input and output of the results, but all the processing is happening outside of the tool, and here we need days, weeks of work, resources by local partners. Of course, this effort pays back because the results of level 3 are the full and comprehensive results of the model, having all the indicators the city would need to ask. So somehow, if a city wants to go through all the levels, it can use level 1 to somehow define the scenarios that they want to analyze on the other levels. Level 2 to define the optimal layout for the supply side, and then level 3 to run the simulation. So all the levels together are facilitating and reducing the execution time of any city willing to have different scenarios, results, and to compare. So these were the two main principles, and after many iterations with the cities of the project, with cities not part of the project, we understand that somehow we achieved, or we managed to have them on our tool. The next two slides will be presented by Athina, which are about the level 3. And level 3, unfortunately, we cannot show it live, as we will show level 1 and level 2. We will only show the interface to the results, so you will see what you will receive or what you will see from the tool. But to understand how it works internally, it will be Athina presenting the next two slides.
Thank you, Josep Maria. So I will keep it brief, mainly just to show you what are the main inputs and processes in order to be able to conduct the simulation analysis of any potential configuration of any shared mobility service of interest that we want to examine. So as Josep Maria already mentioned, we need information, detailed information with respect to the demand. For example, the requests, their specific origins and destinations, the time they want to make their trip, and any potential constraints that they may have. And this information can be obtained from the methods that Sergio also mentioned this morning that were developed by different partners in the project. Then, of course, we need information related to the network, because we need to import in our in the simulation environment the network and the area that we want to investigate. So, for example, it is flexible. The tool gives the flexibility to use travel time information in order to inform the operator about their trip solutions that they will provide to execute the requests. And this information can come from external data sources like floating car data, or even from the simulation environment itself. And given the fleet planning and optimization algorithms that have been developed within the project, we can derive the optimum, let's say, service area or fleet characteristics, for example, the size of the fleet or the capacity of the vehicles, but also how the vehicles are going to execute the requests. In the case of the DRT service, for example, which vehicles will be assigned to which requests, what will be the route that the DRT vehicles will take, and so on. And in the case of the bike sharing service, for example, how the rebalancing strategy should be performed. And then we're ready to perform within the service simulation platform Aims and Right any scenario that we want to evaluate, and be able to obtain the key performance indicators related to both the user, so with respect to the travel times, waiting times, but also related to the operator performance. And just would like to show you just a demo from the simulation of a DRT scenario that we have tested in the city of Thessaloniki. It was a low demand area, and where we tested, let's say, how all these trip solutions obtained from the fleet management model can be visualized and simulated in order to obtain the adequate KPIs. So here you can see the blue circles denote the DRT stops where the requests are waiting to be picked up and also dropped off. And the purple moving circle is the DRT vehicle that goes around to pick up and drop off requests. You can see on the right side of the user interface, there is an event log with complete information about the time the request was made, when it was picked up, dropped off, by which vehicle, but also we have information about the occupancy of the vehicle. And once the simulations have been performed, we can export this event log and to be further visualized in the online decision support tool that Josep Maria will show you shortly. Thank you.
Thank you, Tina. Just to mention that when we mention local teams for level 3, an important output of the project is that all the developments are open source. So any local team willing to use them can access to them. So you don't need the partners of the project, of course, to execute level 3. So you can access all developments and adapt them to your software. It's good that within the project we had different environments. We had PTB, we had Ensan, we had even MATLAB doing the modeling. So we are very flexible, and you can really integrate into any kind of model you have all the developments and the models of the project. So this is the last slide, just to give you an overview of what happened within the project. On the left, you can see the cities, the 4 cities of the project: Thessaloniki, Madrid, Regensburg, and Leuven, and the 3 levels. So mostly Thessaloniki, basically Thessaloniki implemented all the services. We were developing the tool and hosting the tool, so we wanted to test all the services. But also the other cities had different tests, mostly in bike sharing or park and ride in Leuven. And it's interesting that most of the cities were able to went through most of the levels of testing the tool, and they had, as Javier said, these discussions internally with the local community, with the stakeholders on the results of the tool, which this is what we want, and I will show you in the demo. So I will close these slides and go to the live demo in 1 second.
Just 1 second, Josep. Before we go into the demonstration, is there anything that you didn't understand, or that the question that you'd like to ask, or a comment so far? Anything? Nothing? Nothing online? Okay. It seems you've been clear, Josep Maria and Athena, so we can.
I have always the doubt if this means that I am clear or that it's not interesting what
always better. It's always better to ask, huh? Okay, go ahead.
Okay, so now I assume you can see a web page. So this is the tool. The tool, starting from the tool itself, is a website. So it's very easy to access from everywhere and from anyone. So this is the first page of the tool, where you have different info about the project, about the tool. There is a video, which is more or less the demo that I will do, so you can see it again and have a more slowly presentation with more insights. And there are some contact details of the people involved in the project and in the tool development. Going to level 1, you have here the 3 levels. We will go one by one. Level 1, you have an initial introduction of the level itself, but there is a manual. So in this manual, it's a PDF file where it explains how to use the tool, how to use this level, what is the input data, what is the format of the input data, and how to understand the results. This is always important. And since we don't have many time, I will do only one test for a kind of bike sharing system in Thessaloniki. So first you select the service. It can be on demand, it can be a vehicle sharing service, it can be station-based, floating-based. We have quite a lot of combinations of it. Then here you select your country. These are the 4 countries of the project, but of course any city can be used for it. And this is important. You can select the area. It's not that we need the whole city. It's not that we need the region. We can apply the tool in any area. So you can go select a predefined area from Google Maps, or you can even do it manually. And you can go to your city and create a polygon that is telling to us that I want to test the system in this concrete area. So this is really flexible, and for level 1 we only need the surface of this area. So at the end of the day, we need that we have this area of surface to test the service. So the next block is about operating the system. We talk about bike sharing system, so it's about maintaining the bikes per kilometer and per hour. So it's operation cost, but also depreciation, all the costs of the operator. Here you have a description of every input, and you have the units, so it facilitates you or the operator to give you the data. We have stations, we have docks, so we need to introduce the cost of the whole system to operate. Then this slider is the result of all the testing within the project, because we saw that CERTH is having already a system and testing the DSP. They were asking why the optimal solution is not close to the real one I have. So this is important, but we are doing a mathematical optimization. So it's almost impossible that we will find the same solution you already implemented. What we did is, since we are balancing the cost of the users and the cost of the operators, we can have a kind of weight to these two costs. So if you want more stations, more docks, so you don't care having a more expensive system to operate, but you want the society to have a better system, you can use a higher weight for the user cost and not for the operator. And this is important. The system is optimizing the whole system cost. So if the cost of the system is 1 million euros, this means that the operator is paying maybe 200,000 euros to maintain the system and operate it, but the users are investing the rest of the money mostly in time. I am waiting for my bicycle, I am accessing to the station, I am riding my bicycle. So we want to see the whole cost of operating the system, because this is the system cost for society. The second block is about the socioeconomic and functional variables of the system itself. So what is the value of time of my user? It's important to know if I will let them wait more, walk more, or wait less, walk less, depending on the value of time that this city or this area will have. Walking speed for the users, traveling speed for the bicycles, and demand. It is important. Level 1 and level 2, demand is an input. This was one of the issues we also discussed with all the cities doing the demo, that they were asking, okay, I would like the demand to be more flexible. I don't want to give you the demand as an input. We need the demand as an input because we are creating the best supply for this demand. But still, we added, and one of the results you will see is facilitating this issue with the demand. Then it's about the constraints. I am the city authority, I am the transport authority, and I want to keep up to 3 minutes of waiting time on average. Level 1 is always on average, and up to 8 minutes access time to the station. So I can control, I can change these values. And then we come to the decision variables. I need to know how many stations and how many docks. And we can define the threshold that we want to analyze, because I may want more than 20, less than 100, so I can put here the threshold. So now I am clicking calculate, and the system is calculating now in real time, is optimizing with all these values, and it will bring us 3 kinds of results. The first result is this section, which is composed of the optimal values. So for this city, for this area, for these input variables, the optimal solution is 22 stations of 17 docks each, so 180 bicycles. So this is the solution, the optimal solution. If we implement this solution, we adapt this solution, we will have a system with a cost of close to 700,000 euros per year, which 500,000 is for the users, waiting, walking, cycling, and close to 200,000 euros for the operator. This is important. The city has an initial estimation of the cost for the operator if they need to tender the service. And then we can see the constraints if are respected or not. With this layout, we are giving a service with an average of 2 minutes waiting time, 3.2 minutes walking time. So we see that it's acceptable for my citizens and it's okay. Then the second part of the results, because this is really some kind of pool. If you want to discuss this, and this is important, we wanted this tool to be used by the local community. So if we want to discuss with the different actors, the mobility actors of my ecosystem, this is some kind of pool, 22, 17, and 820, that's it. So we created the second set of results, which are the graphs showing the solution space, so from 1 to 100 stations, from 1 to 50 dogs per station. This is the solution space. So here you have all the cost of the system for all the combinations. The optimal one was 22 and 17. 22 stations, 17 dogs. So 22 stations, 17 dogs somewhere here. This is the mathematical, strict, rigorous, optimal solution. But, and I know the cost is 700,000 euros, but I can move through the graph and see, okay, if I don't want 20 stations, but I want 40 stations, I see that my cost will be increased by 50,000 euros. So maybe I can accept this. What does this mean? That this 20,000 euros will be mostly, sorry, for the operator, from 170,000 euros, the cost will be almost double. But doing this, I will reduce for the users their cost from 500,000 to 400,000 euros. So I can investigate, I can discuss, I can go through different combinations of solutions and have exactly these results. So this, we understand that this facilitates the discussion with the citizen associations, biker associations, the potential providers of the service, trying to find, if this is not the solution that we like, we can find a different one, but we keep control of the cost for the operator, the cost for the users, and of course, the waiting time. So if I have more dogs, I am reducing the waiting time from 1.5 minutes to 1 minute. So I control and I know at every moment what is the impact of my decision. The access time from 3.2, we can go to 2.3. So we understand that this will help a lot this discussion. They can navigate these graphs, they can show them live and end up on a consensus on these results. Of course, you can save it as a PDF, you can send it, and you can use it for presentations and anything. So this is level 1. There is a third component, which is the sensitivity for the demand. And now the system is estimating only the optimal values, but for a range of the demand between 20% less and 20% more. So you remember that we introduced 50 trips per hour as our demand. But if the city is not sure about this 50, we can have this threshold, so between 40 and 60. And now what we're having here is the same results for the optimal solution for 40, 45, 50, 55, and 60. So the city can know that, okay, my demand is 50, but it's between 40 and 60. So I know that my system will cost between 600,000 euros and 800,000 euros. I know that I should have between 19 and 23 stations. So this gives a better understanding to the city by providing thresholds and not exact values that they should implement. Then this is level 1. It was just a matter of a few clicks and a few minutes, I would say, to run this scenario. So anyone can run many scenarios in a few hours, and then they can present the scenarios, they can have the different results, indicators, and pick up the ones that are maybe the more interesting for the city. Then we can go to level 2. Level 2, again, we have a manual, how it works, how it can be used. There is a demo of level 2, a demo tool, but this is the normal one. And now we will continue with the bike sharing. In this case, we select the bike sharing system. And here we are not introducing data as numbers, as we did before. We're introducing files with data. In this case, since it's a bike sharing system, we need the demand in one of the two different ways. It can be trip data, and it's the one I will use. So in level 2, for the scooters, I am using trip data. This trip data is a list of origins and destinations and time of trip from our local operator. So if you have this kind of data, you can use it because this data is the real demand. Not the real demand, it's demand that is satisfied by the system, but is quite close to the demand that you may have. If a city has not this data set of trips, it can introduce an origin destination matrix and the zones. And then we will use the module for the incentive population of the project and create ourselves the trip file. We can also introduce the bike lanes network and the public transport stations network. You will see later on why we need these two files. So I will bring these two files as well. Of course, you can download a sample of the dataset, so you know what's the exact format, and you can create the one for your city. Or in the case of the city, the parents of the project, you can go to the repository we have on the project and use the data that is already there. Then I will submit my input and will tell you about this. This input file with the origin destination matrices and the trips is mostly for the patterns, meaning we don't care if the total number of trips in the OD is 100, 1000, or 1 million. We need the pattern, the distribution in space and time of these trips. Here is when you can introduce the absolute value. We do this because if you want to test different demand levels, there is no need to change your input files. If you want to test sensitivity of the system to the demand by 10%, 20, 30%, no need to create many files. You can use the same file with the same mobility patterns and just change here this number. My demand is 1000, my demand is 50% more than 1000. Of course, if you want to change the patterns, you need to introduce a new file. Then the first step is just a visualization of the input data. So you can check that the input data seems okay, especially when introducing all the matrices. It's good to see what is the result of the synthetic population model. So here you can see the origin distribution on a heat map and the demand distribution on a heat map in Thessaloniki. We can use also we use the time dimension, so you can have 24 OD matrices, and here you could see the change on this heat map during the day just by playing the video. Then let's go to step 2. Step 2, we will need a little bit more of time, so I will try to reduce the possibilities. Okay, step 2, what's doing? Once we have this heat map, meaning I have all the origins and all the destinations, in this case, I need to create the set of candidates. So I need, before going to the last set of the final set of stations, we start creating the candidates. So we defined the maximum walking distance. So anyone willing to take a bike, it should not walk more than 300 meters. So we will create a network of stations respecting this constraint, that anyone in my city should be as close as not far away than 300 meters to the station. We can give a threshold that I want my set of candidates to be between 100 and 150. And the search step is just to speed up. So I can look one by one. So I will need to run 50 times the system. I can go 5 by 5, 10 by 10. So I suggest to do it 5 by 5, but here we do 10 by 10 because it needs a little bit of time. I remember that everything is running in real time. So this processing time is because we are doing the clustering of all the original destinations to end up with the list of candidates. And this is it. Here we can see that we have 132 candidate locations, and these are located in my city, and you will see that they follow the patterns of the demand. They are mostly in the seaside area where most of the trips are happening, but still they cover the whole city and in a kind of grid. So everyone has accessibility to the stations. These are the set of candidates. This is the function that is telling us what is the best set of candidates. So it's between 110 and 130. Somewhere here, this is the metric of the clustering performance. Then you can save to JSON any step, so you can have the locations and use them. Now, we should select between this set of candidates and the set of the final configuration. So here we can have some kind of penalty when the station is far away from a bike lane, for example. A penalty when the station is far away from a bus station. This is good for 2 reasons. In the case of the bike lanes, I am helping the users to access to the bike lane network. So it will be a safer system, and I will not have stations far away from the bike lane network. In the case of the bus stop, I am trying to give some kind of multimodality. So if the stations are close to the bus stops, people will be able to use the bus and then use a bicycle for the last distance all the way around. And for this reason, I needed these 2 files when entering the data. Then I can control the density on the number of stops. I can come from level 1 and say I want 22 stops, or I can let the system giving a kind of density constraint tell me how many stops do I need. So now here we are solving the facility location problem using the set of candidates with all these penalty functions and weight functions to find the best layout. Here we are giving as well the minimum and maximum number of dogs. So I want a system with between 300 and 600 dogs. Sorry, and the minimum and maximum number of dogs per station. So I want my stations to be between 5 and 20. So we can control the maximum size and the minimum size of the stations, but the total number of bicycles, dogs I need on my system. So all these inputs can come from level 1 and can be used here. And this is the result. From the 132, it ended up in 22, which totally by chance is what we had in level 1. Is the first time that it happens. And these are the stations. So the 22 locations coming from all the penalty constraints and everything are this one. So it seems that the best configuration for the city for this demand, but this demand, as you saw, is with spatial and time distribution, is this set of 22 stations. And of course, I know that I need a big station with 20 dogs here, a big here with 20, a big with 20. It will be mostly with 20 since we have a few stations. In other runs, we have up to 50 stations and they are 5, 10, 20 dogs each. So again, I can save this file to a JSON. So I have the locations, and of course, these locations, then they can be moved by the city a few meters up, down to find the final location. But somewhere here, these 3 stations, which this is the real city center and there is a lot of demand, we should have these 3 stations. The city could put all them together in one station. So of course, the city needs to fine tune the results of this tool. Finally, the last step is once we know the demand, once we know the stations, we can go one step further and give at least an insight to the operator how much will it cost to balance the system, because the operator knows the number of stations, the number of dogs, the number of bicycles, so it can estimate the cost for operating, maintaining, depreciating the system. But in order to have an understanding of the rebalancing needs, which is an important operation cost for the operator, we are doing this last calculation. So if we accept a system with up to 5 hours rebalancing, so routes running for 5 hours, I want to have between 2 and 6 vehicles running in the city doing the rebalancing, and the speed is 30 kilometers per hour because it's a city area. The system says that, okay, from the historical data, from the demand, from the capacity of the stations, it seems that you will need 2 routes. These are the 2 routes, and the route is giving us the sequence of stations that each track, each van should visit. So you can have 2 tracks doing these circular routes during the whole day and rebalancing the bikes in order to better satisfy the demand when we have directed use of the system. So here, with all this input, we understand that the operator can have a good understanding of the cost of operating the system, but also the city and the authority can have a good understanding of the tendering. I need to tender the system for 1 million, for 500,000. We understand that this is all as important for the city. And then a few metrics about the final working distance, which is 200 meters, and we respect what we had. Of course, this is an average. This is not a maximum or minimum. The density of stations, the number of rebalancing vehicles, the number of stops, so different indicators. So this is level 2.
Josep, I will ask you to wrap up in 3 minutes. Can you do it?
In less than 3 minutes. I am there. Okay. So the result of level 2 is the supply layout that it will come to level 3. So then, as Athena showed, then we can take this supply, we can take the OD matrices, we can run simulation, it can be used in AIMSAN, PTB, any kind of software. And then once we have run offline this exercise, we can come here, we can say, okay, for Greece, for the bike sharing system, I have the results of level 3, and which I can just plot here, the bike sharing, the results, and this is just visualizing. Here we're not calculating anything, everything happened offline, but you can visualize because again, you can use this tool to talk to the local community and tell to them This is the optimal set of locations, the black ones. And from my simulation, the green persons are the origins, the red are the destinations. So I can have a good visualization of what will happen, what is one of the runs of the model in my city. And then I know that I will have 75 requests and I will fulfill all of them. So no one will have no accessibility to a station. And I will know trip by trip duration, time of start, time of ending of the trip. Sorry. And I can plot everything this into maps. I can put it on the map or not. I can extract all this data. So it's interesting, and I have some the distance of every trip. So this is it. And then this is the way you can use the tool. You saw level 1, level 2 in 20 minutes. We use both of them. Of course, level 2, you need to prepare the data. And level 3, if you have this local partner, you can use the tool to visualize and to communicate the results of the exercise.